Raspberry Pis. So this is something that often comes up. So when I'm doing my training sessions and talking to people and whatever, somebody always says, well, emulators are all very fine because we do stuff in cuttlefish or goldfish or whatever, but wouldn't it be nice to use some actual hardware? So there's plenty of hardware out there. There are plenty of options, but somehow the topic always comes round to Raspberry Pi. And why is this? Well, Raspberry Pi basically, for better or for worse, is a standard. Everybody knows what Raspberry Pi is. And so there's a kind of an implicit expectation that, well, why wouldn't we just buy a Raspberry Pi and throw this stuff on there and see what happens? So I've been using Raspberry Pis for a while. Mostly I was using Raspberry Pi 3s some little while back. And I've done some fiddling around with the Raspberry Pi 4s, but because the pandemic intervened and you can no longer get the damn things, that whole thing kind of got a little bit stalled. So what I'd like to do is to propose and to go through some of the arguments for resurrecting that work and have a look at what is necessary to make AOSP to work on Raspberry Pi. So we're talking about the Raspberry Pi 4 because this is the one which has the memory and the hardware capable of running Android. Raspberry Pi 3 is kind of borderline. It never really worked that well, mostly because it doesn't have enough RAM. But with the Pi 4, you've got options and you can get up to 8 gigabytes of RAM, or even 4 gigabytes is good. It's got powerful processors. It's got USB, it's got Ethernet, it's got Wi-Fi, it's got Bluetooth. It's got 2 HDMI outputs, although I've only ever managed to get it to work on one so far. It's got DSI connectors and CSI connectors for cameras and LCD screens. And of course, it's got the wonderful little header here for hats and whatever. So you can plug in all kinds of SPI and I2C stuff to do interesting things and make things flash on and off. So it's a nice hackable little platform. So hasn't this already been done? And the answer is, of course, yes. So the main repository here, I think, really is the Android RPI repository. So a guy called Peter Jung, I think, if I remember correctly, has been doing this for quite a few years now. He's been supporting Android, at least since Android 8, as I recall, maybe earlier. So that's a great repository. Snap Automotive, as we've just been talking to Al Sutton from Snap, they have essentially a fork of Android RPi, which has an automotive build. There's also the stuff being done by Consta Kang. He maintains an unofficial Lineage OS build, and the latest for Android 13 is that link there. And yes, there's even a Google group for discussing Android on Raspberry Pi. However, wonderful that all these things are, they don't do the full AOSP thing. I'll explain what I mean by that in a moment or two. So what I would like, really as an educational tool more than as much as anything, I would really like a platform which implements a clean copy of Android and has builds for tablet and automotive and maybe TV. I'm not so interested in TV, but other people may be. Amongst other things then, I would really like to have SELinux running in enforcing mode, rather than hacking around and doing everything in permissive mode. I would really like it to pass CTS and VTS, the test suites. Maybe not every single thing, but at least some of it. It should really have the modern way of installing firmware. So it should have a super partition, and it should then use logical partitions for the system and the vendor and such like. Really, we need AB partition slots so we can do over-the-air updates. We need a recovery mode. It'd be really great if we had a GKI kernel, so that's the modern way of doing kernels in Android. Be nice if it supported AVB, Android Verified Boot. And a thing I particularly like is the idea of using ADB over a USB cable rather than having to do it over Ethernet, which I always find breaks at some point or other. And if you're doing ADB over USB, you may as well also do Fastboot. So with Fastboot, that means I can reprogram my Raspberry Pi without having to fiddle around taking the SD card out. So this would be my ideal Android Raspberry Pi implementation. So I've thrown something together. And when I say thrown, I mean almost literally thrown. I actually did it this afternoon. So I haven't actually checked to make sure this actually downloads and builds, but I think it probably does. In my local repository, which I generated this from, I have something which kind of works, and I'm not that happy about this. I kind of thought to myself over the Christmas period, this is an ideal time to sneak away from the family once I've eaten all the mince pies, and just kind of work on this quietly while nobody's looking and everybody's sleeping or watching TV or something. Anyhow, that didn't actually happen for various reasons. So what I've got is something which it builds, and that was a bit of a challenge. It boots as far as the Android daemon level, the native level, but then it goes belly up when it tries to load the system services. So there's something wrong in there. There's certainly some issues with the HALs, which I suspect is why system server is not running. But I literally got this running like 12 o'clock today, midday today, and I've not really had a chance to fix it since then. So I put this out there because I'd like this to become a framework, and if nobody else works on it, at least I will continue doing so. Things to consider. So these are areas where we have to think about what you're doing and how it fits into the Raspberry Pi environment. So first of all, booting Raspberry Pi. Raspberry Pi then has its own, well, there's the primary bootloader that's built into the chip, and then there's the secondary bootloader, which is actually these files here, fixup4dat and start4elf. This is all proprietary stuff. We don't have the source code to this, and obviously it knows nothing about Android. But we need a whole bunch of integration to make Android work correctly. Luckily, the U-boot project does most of this stuff for us. So if we take the standard Raspberry Pi boot files, use that to boot U-boot, and then U-boot boots Linux and Linux boots Android, we then should have a pretty good boot environment. So U-boot has support already for the BCB, which we need for recovery and also for doing the over-the-air update integrations. It has stuff for A/B slot handling, so you can tell it to boot from the A slots or the B slots, which is part of the OTA thing. It understands the boot.image format, and that's necessary in particular so that we can have A and B partitions for boot image, and then we can do over-the-air updates. It has support for AVB, although I've never actually tried it, and it has support for Fastboot. So you can get the Raspberry Pi firmware from this place here, download it. You actually only need these two files here. Unfortunately, when you download this entire repository, it's 27 gigabytes. And again, you take out about ½ megabyte for these two files. But this is the canonical place to go get this stuff. And U-boot is U-boot. So this part works pretty easy. And I've thrown together a simple little U-boot boot script, which will load an image and a bootloader. So load an image and a RAM disk, I should say, from the bootloader partition. There's still a lot more stuff to do here. The first few bits are fairly straightforward. So to get it to use the boot image instead of just loading individual files from the bootloader partition is pretty simple. Implementing recovery mode should be pretty simple. I think the A/B slot handling should be relatively straightforward as well. AVB, I haven't really thought about too much. That could be easy, it could be hard. I suspect it will be hard. Making Fastboot work should be pretty easy. So there's a bunch of stuff there, all good fun. Kernels. So right now, essentially what I've done is I've grabbed some stuff from the Android RPi project, and one of those things is their kernel. So their kernel is, it's a modern kernel, so it's a 5.15, which is good. It's based on the upstream Raspberry Pi kernel, I think. And they've done some integration into the latest Android kernel build tools. So it's using build.sh to build the kernel, and it's using repo and such like to integrate the kernel and so on. But it's not a full GKI. In fact, it's not a GKI at all. It's a completely custom kernel image. So to be done here, the main thing would be to switch to using a generic kernel image. So if you're not familiar with GKI, the basic idea here from the Android developers is that there is a single kernel binary called the generic kernel image, which runs on all Android systems. Well, okay, there are two of them. There's one for ARM and there's one for Intel. And then everything that is not in the generic kernel image is moved out into what they call vendor modules. So you have a bunch of kernel modules, which you then load into the GKI at boot time, and hopefully everything works. So the main job here would be to recode all of this stuff and move it into vendor modules. I've not sized this in any way. I suspect it's a huge amount of work and probably not worth the effort. But it would be nice to do all the same. It would be nice at least to investigate it and kind of size the project. Storage layout. So this is on the SD card. So right now I just have a pretty standard, pretty simple layout. So we have 4 partitions: bootloader, system, vendor, user data. But this is not really a normal Android layout. So what we'd like to do is to switch to something like this. So we need a MISC partition to store the bootload control block. We'll have the kernel and RAM disk in the A and B partitions. We'll have VB meta to store the metadata for AVB. We'll have the big super image, which contains pretty much everything else, and then user data. And ideally, we'd switch to using F2FS, the flash-friendly file system, rather than the boring old ext4. At the moment, then, I have a script which will write this format, the now format. But as we add these various bits in, we can just extend this. And then the actual configuration of the device in AOSP. Now, for those of you who are firmware or AOSP developers, you'll know this is always a fun thing to do. I was trying to start from a clean state. So I literally started with empty directory and started piling stuff in there. And there isn't an easy way of doing this. Somebody said to me, oh, just base it on Cuttlefish. Cuttlefish is the cleanest implementation you have. So I started with Cuttlefish, and there's still some Cuttlefish stuff in there. And this is kind of the Google way of doing things. This is how Google think you should put together a device, except that there's a lot of stuff in there which is very specific to the way Cuttlefish works. It's frankly not very modular, and you end up hacking around quite a lot. So I started with Cuttlefish and hacking around a bit. Then I started looking into the Vim3 support. So the Vim3 is a nice little board which is fully supported actually as part of AOSP. So I cribbed some stuff from there. And of course, I looked at the Android RPi project for the kernel and various other things that are necessary to make Raspberry Pis work. So I've kind of, what I've ended up with then is kind of a mishmash of all of these 3 things. And if somebody asked me to do it all over again, I don't think I could, because I didn't document every single step, except it is what's there in the Git repository. So right now we have device A for RPi. So this is Android for Raspberry Pi. I'm not hugely pleased with this, but that's what I ended up with. And if you look within there, there are currently 2 products. There's RPi for tablet and RPi for auto. Quick mention about the graphics for the Raspberry Pi. The great thing here is that Raspberry Pi has good support from the Mesa 3D project. So it has open source graphics drivers, which work pretty well. The main issue here is that Mesa 3D is shipped with AOSP, but it's the wrong version, or at least it's not a version that's compatible with the Broadcom chip. So you need to replace that with a later version of Mesa 3D. And again, I cribbed this from the Android RPi project. Quick mention about ADB over USB. So this is this is a thing which I think is quite neat, although maybe other people may not agree. But the basic idea is you can plug a USB cable in. You don't need a network. Quite often the networks don't work and whatever. And I can then just use a ADB shell and it should just work. The main problem with this, as I discovered, is that the port you have to use is the USB-C port on the Raspberry Pi board. And that is essentially is the power supply for the board. And it requires about 2 amps, depending what you do with it, which is quite a lot. So if you take a standard USB cable, plug one end into the Raspberry Pi USB-C port and the other end into just a standard PC port, you'll find you only get 500 milliamps, which isn't quite enough. I don't have a total solution for this, but really what you need is a separate power supply to supply power to the board, which you can do either through the GPIO headers, or maybe you could even use power over Ethernet or something else. I hadn't really thought about this in fully, but I did have a working version of this, but then I unfortunately broke it sometime in the last couple of days, and it currently is not working. And then finally, Fastboot. Once you have this part working, Fastboot comes almost for free, so I can use Fastboot over USB, and then I can just do an Android build, and then just do Fastboot flash all. That will reprogram the SD card, probably quite slowly, but at least I don't have to fiddle around plugging and unplugging SD cards. So that is a very quick introduction to what it is I'm trying to do. And as you probably gather from my kind of side comments, it'd be really great if anybody was interested, if anybody could give me a hand.